Year 10. Welcome back to another video from Dr. Beck looking at chemistry. This one is the second in a series of two relating to metallic bonding. So this is video 2. If you haven't seen video 1, please pause, stop, go back to video 1, and then you can follow this. This will make much more sense. Today then we're going to look at the bonding within metal alloys in particular. Video 1 was all about pure metals. This one is all about metal alloys. We're going to be able to describe and explain the properties of metals and metal alloys like we did before. Lots of key words and a key question to get you thinking. When you're ready then, I'm going to give you a few minutes just to write this down, so please pause the video and start when you're ready. Okay, so today then we're going to be looking at metal alloys. Then at the end, a little bit of a summary task about everything we've learned in the last couple of weeks. First of all, what is an alloy and how are they used? Well, here's one example of an alloy being used. This is a metal aeroplane, some kind of fighter jet. And this particular metal is very, very unlikely to be pure metal, because we know of things about pure metal, and that's not suitable for an object like this. So we're looking at what we call a composite material, an alloy. Alloys are mixtures of different metals. Now, as you see in this list, you might see things which are non-metals, in particular carbon, but in general, when we're talking about metal alloys, we're talking about different metals. Now, at room temperature, most pure metals are solid, so we need to heat them, we need to melt them, and then just like two liquids, we can mix them together. And once that's all homogeneous, once that's all the same composition, they can then be turned back to a solid by being cooled down. You need to know a few mixtures, perhaps just to look at a graph and look at the composition, or perhaps work out a missing percentage composition. So these are most common ones we talk about in GCSE. So we've got steel, stainless steel, which is stainless steel is waterproof, it won't go rusty. Brass, solder, and white gold. Let's turn to our model and we remind ourselves of metallic structure to begin with in a pure metal, and then we will have a look at metal alloys. So we had this idea of these ions, the positive charge part of the atom, the central nucleus with its protons, and we have these outer shell or valence electrons. Now these aren't associated with any particular one atom, they are delocalized. These can move and they can therefore carry charge, and they allow the very rapid conduction of heat, of thermal energy. This was our model. This allowed the metal to be quite soft, bendy. These layers of ions can easily slide through and over each other. We can say that metals are malleable and ductile. We can bend them and we can draw them, we can pull them into wires. So this is our solid metal. Let's pretend we're going to melt this metal. So here we go. We're going to add some thermal energy. We're going to break some of these electrostatic forces, overcome them, and they're going to then resemble the liquid that we learned about probably in Key Stage 3 in Year 7 or Year 8. Now, an alloy is a mixture of elements of metals. And here we go. I'm going to add some more metals. These are in a molten form. And here we go with our other kinds of metal atoms. Remember, they're all going to be molten. Let's just make sure we've got the right number of electrons. That's looking pretty good. And again, we know that in any metal, these electrons are delocalized. So they're not associated with an element, any particular ion, but they are there free, held together with these electrostatic forces. So at room temperature, these are very likely to be solids, these metal alloys. But hopefully you can now see some things happened. That regular structure has now disappeared. We can't get these together in nice, neat, orderly rows. And even if we do, then we end up with roads that don't slide past each other very easily. And this is no good. I can't get one road to slide without it affecting and impacting on other roads. And the whole thing makes this much less malleable. So alloys tend to be much stronger than pure metals. Yes, they still have the delocalized electrons. I'm just going to take those out of the way for now. So yes, they conduct electricity, but metal alloys are much stronger because they don't have these layers of ions that can slide over one another easily. An alloy is much less malleable and much less ductile. So, back to our questions. Can we use these ideas now to answer these questions? We've got this idea that pure metals are very soft because the layers can slide over each other easily. Layers of what? Well, layers of ions. If you add an atom of a different element, a different size element, different size biscuit, it will have a different size and disturb the layers. So I'm going to ask you to answer these 4 questions. Question 104 has got 3 parts. Use keywords. Pay particular attention to the number of marks in each case. This gives us a clue of how much we need to write, how many keywords we're going to need to involve. First one, explain how electricity is conducted in a metal. Description of structure and bonding. Describe how the structure of an alloy is different from the structure of a pure metal. And ideas about the structure and the properties of copper and iron. So I'm going to give you 8 minutes, should be enough for this, maybe 10, but whenever you're ready, just come back to the video. So please pause now and have a go at these questions. Okay, welcome back. Let's have a look at the keywords we're going to need for this. So this is just about electricity. So we don't need to talk much about the malleable nature and the ductile nature of metals, or indeed the thermal conduction of metals. We're just going to talk about electricity being conducted. So we say metals consist of lattice positive ions surrounded by delocalized electrons which can move and carry charge through the whole structure. Okay, so the keywords we're wanting are this lattice idea, positive and negative. We've got delocalized, which means they can move, and carry charge. Those are 4 marks. Second one, 102. Describe the structure of an alloy and how you describe how it is different from the structure of a pure metal. Okay, pure metals have regular rows of ions that slide past each other but In alloys, this regular pattern is not present. Okay, so we've described and we've said one is and then the other one is. So we've described the difference there. So we've described one, then we've described the other, and therefore compared the two. Moving on, suggest one reason why coins are not made of pure copper. Well, they could be, even though copper is quite expensive, they could be. However, pure metals are soft. Coins need to be durable. Coins need to be harder. We don't want that coin to be folding and twisting. We want them to be hard, so they're made of an alloy. 3 questions about iron. Iron, the element. So this is quite a tough one. We've got to link the structure and bonding to this. Iron has 3 delocalized electrons. Okay, again, that move and carry charge. Can move and carry charge. Allows the body panels to be bent. So this is this key word malleable. We say that pure metals are malleable. So malleable. Iron has ordered rows of ions which can slide past each other. Okay. Next one is about strength. Okay, they might be soft, but still they are quite strong. This is because there are strong electrostatic forces between positive ions and the electrons. Okay, so in 104 we have linked a particular feature of structure and bonding to a particular property, whether it can conduct electricity, whether it can be bent or is malleable, whether or not it is strong. Make sure we're linking the right feature to the right property. So we've got electricity, its malleability, and its strength. Good. So today then we've been looking at pure metals, and we've looked at the difference between pure metals and alloys of metals, or metal alloys, and we've then been able to describe the properties of metals and metal alloys. We're now just going to do a summary task based upon everything we know from the last couple of weeks. So have a look in your booklet, you'll see this table. I'm going to go through the first 1 or 2, and then you can have a look and do the rest yourself. So here we have a table with 5 substances. These are not the element symbols. They're just A, B, C, D, E. We could have used 1, 2, 3, 4, 5. However, we haven't. In each case, we've got a melting point and a boiling point, and then information about the state in which it conducts electricity, if it does. Okay, so we've got all these things going on. And at the end, we're asked to write the type of structure and bonding. We're asked just to choose from 4 things. So either simple molecular, giant covalent, giant ionic, and metallic. So let's look for the clues. Substance A has got a very high melting point. So that tells me it's probably not going to be a simple molecular covalent structure, which are usually gases at room temperature. This will be a solid at room temperature. When it is solid, it conducts electricity, and it also conducts electricity in a liquid form. However, it does not dissolve in water. This conducts electricity. Now, it has therefore free charges that can move around, and in this case, this was going to be delocalized electrons. This will be a metal and therefore have metallic bonding. Okay, next one, let's do one more, give you some clues. Melting point of B minus 107 degrees C, the boiling point is 13. This is the point at which it turns to gas. So at room temperature, this substance would be a gas. It does not conduct electricity in any of these three instances. Therefore, this is telling me this is a covalent molecule, a simple, oh my goodness, simple molecular. I don't know what this substance is, but I know that it would have these types of bonding. Okay, the rest, give yourself a few minutes, have a look at those clues and come back in a couple of minutes. So pause the video. Okay, Year 10, let's go through these. Here we've got something which is a very high melting point and an even higher boiling point, very, very high. It does not conduct electricity in any of these things. So this is probably likely to be something like diamond or quartz. This is going to be a giant covalent structure. Okay, give yourself a tick if you got that. Next, again, another very high melting point and a high boiling point. This does not conduct in a solid form, so this could be giant covalent. However, it does conduct electricity when it's in liquid or in solution. So this will be a giant ionic lattice. When we melt or dissolve an ionic compound, substance, those charged particles, those ions become free to move, and the movement of charge is electricity. Last one, a little bit tougher perhaps. We've got quite a high boiling point here, but the clues are here in the rest. So this is going to be a covalent structure. Okay, it does not conduct electricity when it's in a liquid form. Now, this is still quite a relatively low boiling point. Okay, this is going to be a liquid at room temperature, and this is another simple molecular substance. This is a covalent molecule. I happen to know this is benzene, C6H6, but it is a small molecule with covalent bonding. So well done if you got those three right, and that's the end of our review. Okay, so go back, check through your notes. If you missed anything from video 1, go back through video 1 and have a look at those ideas. For now, thanks for watching.